Welcome to the channel. Before we begin, I'd like to ask you to support the project by subscribing to the Telegram and YouTube channels. Click the bell to receive all notifications, like the video if you found it interesting, and leave comments. You can also follow the links in the video description to articles and read them. This will greatly help the channel.
You know, deep inside almost every piece of modern technology you own, there's this hidden paradox. We're about to pull back the curtain on how the very components built for silent, perfect precision can actually be listening to everything happening around them. All right, so let's just jump right in. I mean, it sounds kind of crazy, right? The idea that the circuit board in your phone, or your car, or in critical medical gear could act like an accidental microphone. How is that even possible? Well, it's definitely not by design. It happens because of a really subtle and honestly fascinating quirk of physics. So, this weird effect actually has a name. It's called microphonics. It's basically when physical vibrations, sound waves from your voice or even the hum of an appliance, literally get turned into rogue electrical signals inside a circuit. This unwanted noise messes up the pure, clean signals that our electronics need to work, and it can cause all sorts of mysterious glitches. But the big question is, how can a solid chunk of fiberglass and copper possibly hear anything? Well, to figure this out, we're not heading to some high-tech lab. No, we're going way back in time to an 18th century physics experiment that used just two things, sand and a violin bow. Yeah, we're looking at the work of a physicist named Chladni. He discovered something absolutely fundamental about how pretty much any surface vibrates, and it's really the key that unlocks this entire mystery. His experiment was so simple, it was brilliant. He just took a metal plate, sprinkled some sand on it, and then, get this, he vibrated it by dragging a violin bow along the edge. And what happened next was just mind-blowing. The sand didn't just rattle around, it organized itself into these incredible, almost magical geometric patterns. So what was happening? The sand was actually getting pushed away from the areas of the plate that were vibrating like crazy, and it started to pile up in the spots that were perfectly still. And these quiet spots, they're called nodal lines, and they basically create an invisible map of the vibration. And this is the real aha moment. Because a modern circuit board, it's basically just a super complex version of that same metal plate. It has its own unique set of resonant frequencies, and when sound waves hit it, it flexes and vibrates in these very same predictable patterns. Okay, so the board is vibrating, got it. But that's just, physical movement. How in the world does that turn into electrical noise that can screw up a circuit? Well, it turns out there are actually three main ways this happens. First step is something called the piezoelectric effect. Yeah, I know, it's a bit of a mouthful, but the idea is actually super simple. A lot of the tiny ceramic components on a board, called capacitors, are made from materials that literally create a little bit of voltage when you squeeze or stretch them. So as the board flexes, they get stressed and poof, instant electrical noise. Okay, second, the board itself starts acting like a tiny little microphone, a condenser microphone to be exact. And it's one you definitely don't want. It's wild when you think about it. As the board bends, the microscopic gaps between all the conductive copper traces change. This messes with an electrical property called capacitance, and that, in turn, creates yet another source of noise. And number three, well, it's something we've all experienced. Good old-fashioned friction. On a microscopic level, as the board vibrates, its different layers and all the little parts on it are rubbing against each other. This creates tiny bits of static electricity that can easily leak into the most sensitive parts of the circuit. All right, so we've got these three tiny microscopic things happening. But you might be thinking, does this really matter? And the answer is, oh yeah, absolutely. Let's take a look at how these phantom vibrations create very real and very frustrating problems in the tech we all depend on. So, the real trouble starts when you hit what's called resonance. This is when a sound wave, let's say the hum from a nearby fan, perfectly matches one of the board's natural vibrating frequencies. When that happens, boom, the vibration gets amplified like 10 to 30 times. A harmless little hum suddenly becomes a huge source of interference. And what's the result of all that? Well, just look at this. On the left, that's the beautiful, clean signal that an engineer is supposed to see. But on the right, that's the same signal, but now it's totally corrupted with microphonic noise. A device might see that phantom noise as real information, which could make a high-end stereo sound terrible, or even worse, cause a sensitive medical instrument to give a completely wrong reading. And you know what's so frustrating for engineers? Sometimes the most common ways of designing a board actually make this problem way, way worse. Like, a classic mistake is putting those noisy little ceramic capacitors right smack in the middle of the board, where it flexes the most. That's like deciding to put a microphone right next to the loudest speaker in a room. Okay, so we get the problem, but knowing is only half the battle, right? How do you actually fix it? How do you design for this? This is really what separates the good stuff from the stuff that only works in a quiet lab. Let's dig into the engineer's toolkit. Well, the coolest solution, honestly, takes us right back to that sand experiment. Remember those nodal lines, the quiet spots where all the sand piled up? Engineers can do the exact same thing. By placing sensitive components near the mounting points of the board, they're putting them in those naturally quiet zones where there's almost no vibration. Another smart move is just to pick the right parts for the job. Remember how some capacitors create noise when they're squeezed? Well, there are other types. Yeah, they've got these techie names like C0G or NP0 that are basically immune to that. They're made from materials that just don't do it. It's a great way to stop the noise before it even starts. And then, for the really important stuff, I'm talking about things where failure is just not an option. Engineers have some seriously clever tricks up their sleeves. They can use components that have little built-in lead frames that act like tiny shock absorbers. They can even cut small slots right into the circuit board to isolate a critical part from all that flexing. And you know, there's this quote that just nails it. It really gets to the heart of why this matters. Because look, it's one thing to get a circuit to work on a quiet bench, but getting it to work perfectly out there in the messy, noisy, real world, that's a whole different ballgame. And understanding this hidden physics is how you win. So it all comes full circle, doesn't it? Those incredible sand patterns that Chladni showed everyone 200 years ago, they're not just some neat party trick from a physics textbook. They are a literal roadmap for building the reliable tech we use every single day. It really gets you thinking, right? We've just seen how something as invisible as a sound wave can literally shake our technology to its core. So what else is out there? What other hidden forces and silent principles are quietly working behind the scenes, making our entire digital world tick?